Stop the clock, not at 1 billion years, not at 500 million. Stop it here, 280 million years. The universe has completed barely 2% of its present lifetime. If the entire history of the cosmos were compressed into the life of a 100-year-old person, the universe would be only 2 years old. There is no Earth, no Sun, no planets that we know of. Most of space is filled with hydrogen and helium, the simple material left behind by the beginning. The first stars may have only recently emerged from the darkness, and according to many of our earlier models, galaxies at this age should be small, faint, and exceptionally difficult to find. The universe should still be learning how to turn gas into light. But then, we found this. It does not look impressive. It is not a spiral. It has no majestic arms, no glowing disk, and no recognizable structure. It is little more than a faint smudge in an ocean of ancient light. But that smudge is MOMZ14, currently the most distant galaxy ever confirmed through a spectroscopy. Its measured redshift is 14.44. We're seeing it as it existed only 280 million years after the Big Bang. Its light began crossing the universe roughly 13.5 billion years before it finally entered the mirror of the James Webb Space Telescope. Distance alone would have made it exceptional, but distance is not the real mystery. MOMZ14 is brighter than astronomers expected a galaxy from this period to be. It is too compact, yet its light appears spatially extended, suggesting that we are seeing a dense stellar system rather than a single brilliant point. Its recent rate of star formation may have increased dramatically, and inside its spectrum, astronomers found something even more provocative: nitrogen. Not merely the simple hydrogen and helium created near the beginning, but an element that had to be manufactured through stellar chemistry. Its measured nitrogen abundance relative to carbon is far above the ratio found in the Sun. Before that chemical signature could appear, the universe had work to do. Gravity had to gather gas into dark matter halos. The gas had to cool and collapse. Stars had to ignite. Inside those stars, nuclear reaction had to transfer simple elements into more complex ones. At least some of that processed material then had to escape, mix with surrounding gas, and become visible in a new stellar environment. Every step consumes time, and time is precisely what this galaxy did not have. There is another clue. At this stage of cosmic history, the space between galaxies should have been filled almost entirely with neutral hydrogen, a dense cosmic fog capable of absorbing ultraviolet light. But MOMZ14's spectrum does not show as strong an absorption feature as some models would predict. That may mean the galaxy or other nearby sources had already started carving an ionized bubble into the gas around it. The evidence is tentative. It does not prove that the whole universe was already being reionized, but it raises an unsettling possibility. This young galaxy may already have begun changing the state of the universe beyond its own borders. Matter had to assemble, stars had to manufacture new elements, light had to transform the surrounding hydrogen. 3 cosmic clocks, all apparently running faster than many astronomers expected. And MOMZ14 is not the only clue. Webb has uncovered a wider population of unexpectedly bright galaxies in the first few 100 million years, objects appearing in numbers that several pre-Webb models did not anticipate. So what happened? Did the first galaxies convert gas into stars with extraordinary efficiency? Were the earliest stars more massive and chemically productive than the stars forming today? Did violent bursts make young galaxies blaze like cosmic beacons for a while? Could hidden black holes be adding to their light? Or have we misunderstood something deeper about how quickly structure can emerge from darkness? The question is not whether this galaxy exists. Its light has reached us. Its spectrum has been measured. The question is how the universe learned to build so much so quickly. To understand what Webb discovered, we have to follow something almost impossibly small, a single photon, a particle of light launched from a young galaxy while the universe was still in its infancy. It carries no photograph, no written history, no explanation of the world that created it, and yet, hidden inside its wavelength is a record of where it came from, what happened around it, and how much the universe changed during its journey. For more than 13 billion years, that photon traveled through expanding space. Then, after crossing nearly the entire observable history of the cosmos, it struck a sheet of gold aboard a telescope built by a species that did not exist when its journey began. Light is astonishingly fast. In 1 second, it can circle Earth more than 7 times, but the universe is so enormous that even light requires time to cross it. Moonlight reaches Earth in a little over 1 second. Sunlight takes about 8 minutes. The light from Proxima Centauri, the nearest star beyond the Sun, travels for more than 4 years before reaching us. So, when you look into the sky, you never see anything exactly as it is now. You see the moon 1 second ago, the sun 8 minutes ago, Proxima Centauri more than 4 years ago, and distant galaxies as they existed millions or billions of years in the past. The sky is not a picture of one universal present. It is an archive. Every distance reveals a different page of history. A galaxy 100 million light-years away is seen as it was 100 million years ago. A galaxy billions of light-years away is seen during an age before Earth existed. And when astronomers detect light from the first few 100 million years after the Big Bang, they are not reconstructing that period from fossils or ruins. They are receiving light that actually departed during that era. This is astronomy's natural time machine, not a machine that sends us into the past, but one that allows the past to arrive here. The farther we look, the older the information becomes, but distance alone is not enough. Ancient light must survive a second transformation, one caused by the expansion of the universe itself. The universe is expanding. This does not mean that every galaxy is traveling outward from one central explosion into an empty region beyond it. There is no known central point from which all galaxies are escaping. Instead, on the largest scales, the space between distant galaxies is expanding. Imagine dots drawn on the surface of a balloon. As the balloon inflates, every dot sees the others moving farther away. The dots are not crawling across the rubber. The surface between them is stretching. That analogy is imperfect. The universe is not expanding into a surrounding room, but it captures the essential idea. Space itself changes with time, and anything traveling through that expanding space is affected, including light. Cosmological redshift is caused by this expansion stretching traveling light toward longer wavelength. Picture a wave drawn across an elastic ribbon. The peaks begin close together. Now stretch the ribbon. The wave does not disappear, but the distance between its peaks increases. Its wavelength becomes longer. Something similar happens to light crossing the expanding universe. A photon may leave a young star as ultraviolet radiation, but while it travels, the universe expands. The wavelength is stretched again and again and again. By the time light reaches us, it may no longer be ultraviolet. It may have shifted beyond the red edge of human vision and deep into the infrared. This is cosmological redshift. Not simply the ordinary Doppler shift produced by an object moving through space, but the cumulative stretching of the light as the space through which it travels expands. Astronomers describe this stretching with a number called redshift, represented by the letter Z. A redshift of 1 means the observed wavelength is twice the wavelength at which the light was emitted. A redshift of 2 means it has been stretched to 3 times its original wavelength. And a redshift of 14 means the wavelength has expanded to roughly 15 times its starting value. This is why an early galaxy can disappear completely from visible light images while appearing in infrared observations. Its light has not necessarily vanished. It has moved beyond the wavelength our eyes and many earlier telescopes were built to detect. The universe has translated its message into infrared. That is why the James Webb Space Telescope was designed differently from an ordinary optical telescope. Its primary mirror is 6.5 meters across, assembled from 18 hexagonal segments working together as one reflecting surface. That large mirror collects extremely faint light, but collecting infrared radiation creates another problem. Every warm object glows in infrared. Earth glows, the telescope's electronics glow. Even the telescope itself would produce infrared radiation capable of overwhelming the ancient signals it was built to detect. So Webb operates near the Sun-Earth L2 region, approximately 1.5 million kilometers from Earth, while a 5-layer sunshield blocks heat and light from the Sun, Earth, and Moon. Its large segmented mirror and thermal design allow its instruments to detect extraordinarily faint infrared sources. On one side, sunlight and heat. On the other, a telescope staring into cold space. Webb does not merely need to be powerful, it needs to become quiet enough thermally to hear the faint infrared whisper of the beginning. For billions of years, our photon crosses growing cosmic distances. Galaxies form around its path. Stars ignite and die. The Milky Way assembles. The Sun is born. Earth cools. Life begins. Civilizations rise. And throughout all of it, the photon continues. Its wavelength stretches. Its energy decreases. Its original ultraviolet identity is transformed into infrared light. Finally, it reaches Webb. The telescope catches it, not as a visible spark, not as a perfect image of one ancient star, but as one tiny contribution to a measured signal. Combined with other photons from the same source, it begins to form a pattern, a faint point in an image, a break in a spectrum, a clue. The photon tells us that something luminous existed extraordinarily early, but it does not immediately tell us what that object was. A true newborn galaxy? A dusty object much closer to Earth? A cool star inside our own Milky Way? A black hole surrounded by burning gas? Or simply noise that resembles a discovery? At the edge of observation, distance can be deceptive, and the farther astronomers attempt to look, the more carefully they must separate ancient light from convincing imposters. Because finding a faint red object is only the beginning. The next challenge is proving that it truly came from the dawn of the universe. Before galaxies, before stars, before planets, the universe was remarkably simple. During its first few minutes, it produced almost all of the hydrogen and helium that would later fill space. There were also tiny traces of lithium. But something important was missing. There was essentially no carbon, no oxygen, no nitrogen, and no iron. Those elements had not been created yet. The universe had the raw material for stars, but most of the ingredients needed for planets, complex chemistry, and eventually life still had to be manufactured. And there was only one place that could do it, inside stars that did not exist yet. For hundreds of thousands of years, the universe remained filled with hot charged particles. Light could not travel freely through them. Then, about 380,000 years after the Big Bang, the universe became cool enough for electrons to join atomic nuclei and form neutral atoms. Suddenly, light could travel across space. That ancient light is still around us today. We call it the cosmic microwave background. It is the oldest light we can directly observe. But after it was released, the universe entered a long period of darkness. No stars, no shining galaxies, only enormous amounts of mostly hydrogen and helium waiting in the dark. The universe was not perfectly smooth. Some places contained slightly more matter than others, and gravity began exploiting those tiny differences. Regions with more matter pulled in even more matter. Dark matter gathered first, creating invisible gravitational structures. Gas followed. Slowly, small pockets of the universe became denser and denser. Imagine snow rolling down a hill. It begins small, But as it moves, it gathers more material. Gravity did something similar on cosmic scales. Eventually, enough gas collected in certain places for something completely new to happen. The first stars ignited. For the first time since the beginning, the universe had new sources of light. Some of these early stars were probably much more massive than the Sun, and massive stars leave fast. They burn through their fuel quickly. Then they die. Some explode, and in doing so, they begin changing the chemistry of the universe. Inside stars, new elements can be created: carbon, oxygen, nitrogen, and many others. When stars die, some of that material is thrown back into space. Later stars can then form from gas that is no longer chemically pristine. The universe has begun recycling itself, but every step requires time. To understand why galaxies like MOMZ14 are so interesting, imagine that three clocks began running in the early universe. The first is the build clock. Gravity must gather enough gas and dark matter to construct a galaxy. That takes time. The second is the enrich clock. Stars must form. Some must live, some must die, and their newly created elements must mix into the surrounding gas. That also takes time. And the third is the clear clock. Young stars produce powerful ultraviolet radiation. Enough of that radiation must escape their galaxy and begin stripping electrons from the neutral hydrogen surrounding them. In other words, galaxies must begin clearing the cosmic fog. Now look at the time available. By cosmic standards, that is almost nothing, and yet MOMZ14 appears at roughly this moment. So the question becomes, had gravity already built enough? Had stars already enriched enough? Had their light already begun clearing the surrounding darkness? Webb did not merely discover that a galaxy existed this early. It found evidence that all three clocks may have been running faster than we expected. Finding a faint red object is easy. Proving that it comes from the first few 100 million years of cosmic history is much harder. Astronomers begin by looking at the same patch of sky through different wavelengths of light. And very distant galaxies can do something strange. In shorter wavelength images, they disappear. Then, in longer infrared wavelength, they suddenly appear. Why? Because neutral hydrogen absorbs much of the ultraviolet light below a particular wavelength. When that light travels through an expanding universe, the boundary created by that absorption is stretched toward the infrared. So a very distant galaxy can seem to drop out of one filter and reappear in the next. This is called the Lyman break or dropout technique. But there is a problem. A red object is not automatically an ancient galaxy. Dust can make a much closer galaxy look red. A cool star inside the Milky Way can imitate similar colors. Two objects can overlap in the same line of sight. Detector noise can create a false signal. And some lower redshift galaxies have strong emission lines that can confuse the picture. So an image alone is not enough. It gives astronomers a candidate, not a final answer. Think of it like a detective case. A dropout image is a witness statement. Useful, interesting, but not yet proof. This is where spectroscopy becomes crucial. Webb's near-spec instrument does not simply measure how bright an object is. It spreads the light into its different wavelengths. The result is a spectrum. Now, astronomers can ask a much stronger question. Where exactly does the light disappear? If the sharp break appears at the wavelength expected for an extremely distant galaxy, the redshift estimate becomes far more convincing. And if several faint emission lines appear at positions that all agree with the same redshift, the case becomes stronger still. Imaging tells us there may be something ancient here. Spectroscopy asks, does its light actually behave like something ancient? That is the difference between suspicion and evidence. There is an important distinction here. A galaxy selected only from its colors is a photometric candidate. It may be very convincing. but its distance is still inferred mainly from images. A spectroscopically confirmed galaxy has stronger evidence. Its light has been separated by wavelength. The position of its break or other spectral features supports the distance directly. These two categories should never be treated as exactly the same thing. At the edge of the observable universe, that difference matters. Astronomers test candidate after candidate. Could it be dust? Could it be a nearby star? Could it be noise? Could another foreground object be confusing the measurement? One by one, the weaker explanations are removed. And when Webb's spectroscopy began, confirming some of these objects, something unexpected happened. The mystery did not disappear, it grew, because the problem was no longer that one strange galaxy had slipped through the net. More bright galaxies were beginning to survive the tests. Before Webb, astronomers already had a general expectation. The farther back in time they looked, the fewer bright galaxies they expected to find. And that made sense. A galaxy needs time for gravity to gather gas, time for stars to form, time for those stars to build up enough light. So if we look extremely early, only a few 100 million years after the Big Bang, bright galaxies should be rare, not impossible, just uncommon. The early universe should have been dominated by smaller, fainter systems, still in the process of growing. At least that was the expectation. Then Webb began counting. At first, there was one interesting candidate, then another, then more. Some disappeared after better measurements, but others survived, and several were confirmed to be genuinely very distant. The surprising part was not simply that galaxies existed this early. Astronomers expected galaxies to exist. The surprise was how bright some of them were. In several Webb surveys, the earliest bright galaxies appeared more common than many older models had predicted. The exact difference depends on which galaxies are counted, how bright they are, and which model is used for comparison. So this is not a simple statement like, there are 100 times too many galaxies everywhere. That would be misleading. But there's a real pattern worth explaining. At the brightest end, and especially at the very highest redshifts, Webb has repeatedly found more light than many astronomers expected. Why is that a problem? Because brightness usually means something is happening quickly. A galaxy may be bright because it is forming many stars, or because it recently went through a powerful burst of star formation, or because its stars are unusually massive, or because very little dust is blocking their ultraviolet light. A feeding black hole can also add extra brightness. So brightness does not tell us exactly what the galaxy is doing, but it tells us that something energetic is happening. And when many bright galaxies appear very early, astronomers have to ask, did the first galaxies build stars faster than expected? Were their stars different? Or are we simply catching rare galaxies at unusually bright moments? There is another reason not to jump to conclusions. Webb can see incredibly deep, but some of its deepest surveys cover only tiny areas of the sky. That means astronomers may sometimes be looking at a region that happens to contain more galaxies than average. And at these extreme distances, the numbers are still small. If you have only 3 galaxies, finding one more changes the result a lot. Some candidates also turn out to be closer objects, others are too faint for immediate spectroscopic confirmation. So the exact size of the problem is still being measured. The important point is simpler. The unexpected galaxies are not disappearing. As the data improve, some remain. One strange galaxy can be a mistake, several can still be bad luck, but once multiple objects survive spectroscopy and independent surveys begin finding similar systems, the question changes. It is no longer, did Webb find one impossible object? It becomes, are our expectations for the early universe too conservative? That is a much bigger question. Among this growing population, two galaxies became especially important. One showed that a surprisingly bright stellar system could already exist near the beginning of cosmic history. The other went even farther and carried a chemical clue inside its spectrum, JWST-Z14-0 and MOM-Z14. One galaxy can be an accident, a population is a message. Among the thousands of objects Webb has discovered, one tiny point of light became especially important. Its name is not exactly memorable, JADES-GS-Z14-0. When its light began its journey toward us, the universe was only around 290 million years old. Earth would not exist for billions of years, neither would the Sun. Even the Milky Way was still far from becoming the galaxy we know today. And yet, in this extremely young universe, Webb found a galaxy already shining brightly enough for us to detect more than 13 billion years later. That alone was remarkable, but its distance was only the beginning. At first, there was a complication. Another galaxy sits very close to it in our line of sight. That foreground object is much nearer to Earth, so astronomers had to ask, was this supposed ancient galaxy actually real, or was the nearby object confusing the measurement? Webb's spectroscopy allowed astronomers to separate the two. Their light did not tell the same story. The nearby galaxy could not explain the sharp spectral break seen in the distant source. Jade's GSZ14 survived the test. This was not simply a red object that looked ancient. Its spectrum showed that we were genuinely seeing a galaxy from close to the beginning of cosmic history. Then came another clue. The galaxy was not just an unresolved pinprick of light. Its glow was slightly extended. That matters. A single extremely bright object, such as an exposed active black hole, would appear much more point-like. Instead, much of the light appeared to come from a compact collection of stars. Do not imagine a miniature Milky Way. No beautiful spiral arms, no calm, mature disk. This was probably a small, dense, irregular system, packed with young stars and undergoing intense growth. A galaxy is still being constructed while we are watching it. Later observations revealed something even more important: oxygen. The Big Bang did not produce meaningful amounts of oxygen. Oxygen had to be manufactured inside earlier stars. Those stars then had to release it into space. So before the light from this galaxy ever began traveling toward us, other stars had already existed. They had already processed primordial gas, and at least some of their enriched material had already entered this galaxy. The first clock, Bild, was moving quickly, and the second, Enrich, had clearly started too. The galaxy already showed that galaxy formation could move surprisingly fast, but then astronomers found another object, one slightly farther into the past, and this galaxy would become even more provocative. Its name is MOM-Z14. MOM stands for Mirage or Miracle, an appropriate name for a survey searching for objects so extreme that astronomers first have to ask whether they are even real. Webb near-spec instrument examined the object. A sharp break appeared in its spectrum, and several faint ultraviolet features lined up with the same enormous distance. The result placed MOM-Z14 at a redshift of approximately 14.44. Translated into cosmic time, we are seeing it only about 280 million years after the beginning. That is only about 2% of the universe's current age. And MOM-Z14 was not merely distant, it was bright, brighter than many earlier models would have expected for a galaxy at this time. This does not mean it violates physics, but something had to produce all of that ultraviolet light. Perhaps it was converting gas into stars unusually efficiently. Perhaps it had recently entered a short, violent burst of star formation. Perhaps its stars themselves were different. Whatever the explanation, this tiny galaxy was producing an extraordinary amount of light extremely early. MOMZ14 is also extremely compact. Again, do not picture a modern spiral galaxy squeezed into a smaller box. Think of something much denser, a concentrated region filled with intense young stellar activity. Its light is very blue. That is usually a sign of hot young stars. There also appears to be relatively little dust blocking the ultraviolet radiation, and models of its stellar population suggest that its star formation may have increased dramatically shortly before the light we observe was emitted. In other words, we may be catching this galaxy during one of the most active moments of its young life. Webb will keep collecting spectra from the earliest galaxies it can reach. Astronomers will ask, is unusual nitrogen common? Are hidden black holes contributing to the light? How quickly were these galaxies building their stars? And does anything exist even farther back? ALMA can search for oxygen, carbon, gas, and dust. That will tell us how chemically developed these galaxies really are. Future wide field surveys can search much larger areas. That matters because Webb sees extremely deeply but over relatively small pieces of sky. A wider senses can tell us whether bright early galaxies are genuinely common or whether we have simply found a few extraordinary regions. And radio telescopes will attack the problem from another direction. Instead of looking only at the galaxies, they will search for the neutral hydrogen around them. That may eventually reveal when the first ionized bubbles appeared and how quickly they grew.